A tree is a data structure that stores elements in a hierarchy. We refer to these elements as nodes and the lines that connect them as edges. Each node contains a value or data. In this example, our nodes have integers, but in a real application, we could store objects in these nodes. For example, we could have a tree of person objects. These person objects could be part of an organization or a family. The top node in the tree is called the root. As you can see, our root node has two children, 2 and 3. Our root is the parent of these nodes. These nodes also have two children each. The nodes on the bottom don't have any children. We refer to these children as leaf nodes, just like the leaves of trees in the real world. Now, in this example, our nodes have a maximum of 2 children. This is a special type of tree called a binary tree. Just like we have different types of trees in the real world, we have different types of trees in computer science. They're all fundamentally the same, but slightly different in terms of the number of children each node can have and how the values in these nodes can be arranged. In this section, we'll be focusing entirely on binary trees because they're easier to understand and come up in interviews frequently. Once you learn binary trees, you can quickly learn about the other types of trees. Now let's look at a few applications of trees. We use trees anywhere we want to represent hierarchical data, such as a tree of people in an organization or family, or files and folders on your disk. Another application of trees is in databases. Database management systems use trees for indexing, so they can quickly look up data. Another great application of trees is in implementing auto-completion. For example, think of Chrome. Chrome stores all your past web searches in a tree. Whenever you type a query, it tries to match it with previously stored queries. Trees are also used in compilers. Compilers use a special type of tree called syntax tree to parse expressions. Trees are also used in compression algorithms, such as those used by JPEG and MP3 file formats. So as we can see, trees have a lot of applications in the real world. Now let's look at the operations we can perform on trees and their runtime complexity. This tree you see in this slide is a special type of binary tree called binary search tree because it allows us to quickly look up data. In a binary search tree, the value of any node is always greater than the value of its left child and less than the value of its right child. For example, look at the root node. It's greater than its left child and smaller than its right child. You can see this relationship in every node in this tree. But here's a more interesting fact about binary search trees. Look at the root node again. Not only is the left child smaller, so is every node in the left subtree. So these 3 nodes together represent a subtree, with 4 being the root of the subtree. As you can see, the value of all these nodes is smaller than 7. Similarly, all the nodes on the right side of a node or in the right subtree are greater than 7. Again, you can see the same relationship in any nodes on its left and right subtrees. Now, why does this matter? By organizing our data this way, we can quickly look up a value. Unlike arrays and linked lists, we don't have to traverse the entire tree to find a value. Here's an example. Let's say we're looking for 1. We start with the root node. Is 1 smaller or larger than the value of the root node? It's smaller. So we look at the left subtree. We don't care about the right subtree because we know all these nodes are greater than 7, right? So we are throwing out the right subtree and narrowing down our search to half of the nodes in this tree. Once again, we compare the value we're looking for with the value of this node. 1 is less than 4, so we ignore the right subtree and narrow down our search to the left subtree. Finally, we are at node 1. So here's the interesting part. This tree has 7 nodes, but we found our target node with only 3 comparisons, because in every step, we threw half of our nodes away. This is what we call logarithmic time complexity. So whenever we throw out half of our items and narrow down our search, we have logarithmic time complexity. So looking up an item in a binary search tree runs in logarithmic time, or O of log n. What about inserting an item? First, we have to figure out where we should insert this new node. So we have to use our lookup algorithm one more time. We start with the root. Is 15 greater than the root? It sure is, so we look at the right subtree. Now we are at node 9. Is 15 greater? Yes, it is, so we keep going to the right side. Now we are at node 10, so we should add this new node to the right side of the node 10. As you know, finding a node runs in logarithmic time, and adding a new node runs in constant time because we just have to set the link. That means inserting a new node also runs in logarithmic time. The same is true for deleting a node. To delete a node, first we have to look it up and then we'll have to remove it from the tree by reconnecting the edges. Again, this is an O of log n operation. So trees provide a better performance than arrays and linked lists. Plus, they allow us to model hierarchical data. Having said that, if a tree is not structured properly, its performance can degrade to O of n. We'll talk about this in the future. For now, let's assume that all operations in a good binary search tree run in logarithmic time. Next, we're going to see how we can build a tree from scratch.